The universe has always fascinated and mystified humanity. From the night sky filled with stars to the awe-inspiring images of distant galaxies, the cosmos has been a subject of human curiosity and scientific exploration for millennia. With the advent of modern technology, we've been able to capture stunning photographs of galaxies that are light years away. These images, often found on the internet, offer a glimpse into the vastness of the universe. But one question that frequently arises is, how do we manage to capture such clear photos of galaxies, particularly the Milky Way, when we are already inside one of these galaxies? This article, a part of the Midnight Thoughts series, aims to demystify this question and provide a comprehensive understanding of the process behind capturing images of galaxies from within. Before we delve into the intricacies of this intriguing subject, consider a familiar scenario. Imagine you're standing inside a massive football stadium equipped with a phone boasting a decent camera. You're tasked with capturing a clear photo of the entire stadium from an external perspective, ensuring that the photo encompasses the full expanse of the stadium, from one end to the other. What would you do in this situation? The most straightforward answer to this hypothetical scenario is that you'd need to leave the stadium, get some distance away from it, and then capture the photo from the outside. This conventional approach is how most of us would tackle the challenge of photographing vast structures, but can this principle be applied when trying to capture images of our very own galaxy, the Milky Way? To understand the complexities of capturing images of our galaxy, we must first explore the tools and technology we have at our disposal for space exploration and observation. In 1977, NASA launched Voyager 1, a remarkable space probe. Voyager 1 embarked on a journey that took it to Jupiter and Saturn, transmitting valuable photos and information about these distant planets. However, Voyager 1 didn't stop there. It continued its voyage, venturing beyond the borders of our solar system. Voyager 1 is expected to keep traveling through space until its atomic battery depletes in the year 2036. But, how far has Voyager 1 traveled in the vastness of space during these decades? After 45 years of space travel, Voyager 1 has covered a staggering distance of approximately 23 billion kilometers. While this might seem like an immense figure, it's merely a fraction of the vastness of the Milky Way. To put this into perspective, the Milky Way has a width of around 100,000 light-years. To make a meaningful comparison between these numbers, we need to unify the units of measurement, converting light-years into kilometers. 1 light-year is equivalent to approximately 9.2 trillion kilometers, an astronomical number indeed. With a simple calculation, we can determine that the 23 billion kilometers that Voyager 1 has traversed represent a little over 21 light-hours. Consequently, to travel a distance of 1 light-year, Voyager 1 would need 18,771 years, an estimate that brings us to the year 20,793. Keep in mind that the Milky Way spans a width of 100,000 light-years. In light of these calculations, it becomes evident that conventional methods of taking photographs from a distance would not suffice when dealing with the immense scale of our galaxy. This realization raises a perplexing question: how have organizations like NASA managed to present images of the Milky Way and other distant galaxies to the world, given these seemingly insurmountable distances? Does this imply some form of deception or fraudulent activity on their part? In essence, the fundamental issue here is that we cannot employ traditional means of capturing photos of galaxies by positioning ourselves at a distance from the galaxy and capturing images from that external vantage point. Anyone who claims that this is how images of the Milky Way are obtained is indeed misguided. However, the above conundrum does not imply that we are entirely incapable of obtaining external photos of our galaxy. To address this, let's return to the analogy of the football stadium introduced earlier. Suppose we wanted to simplify the process for you, the observer inside the stadium, to capture an image that appears as if it were taken from outside. How could we achieve this effect without requiring you to physically exit the stadium? The key concept at play here is image segmentation. In this scenario, you, the observer inside the stadium, would remain at your position, equipped with a professional camera. Instead of attempting to capture a single comprehensive image of the entire stadium from your spot, you would break the task down. You take individual photos of various segments of the stadium, perhaps a photo of the goalpost, a photo of the right side stands, a photo of the left side stands, and a photo of the other goalpost. These photos would collectively cover all areas of the stadium surrounding you. Once you've captured these separate images, you would then combine them, akin to assembling a puzzle. The end result would be an amalgamation of these photos, creating a composite image that resembles an external perspective of the stadium. It's essential to note that this method, while effective, might not achieve the same level of accuracy as capturing an image from a genuine external viewpoint. The concept of image segmentation, a strategy that enables us to create the illusion of external photographs from within, is precisely what astronomers have employed to capture images of the Milky Way and other galaxies. This approach was not exclusive to NASA or modern space agencies, it has its roots in the work of astronomers and scientists throughout history. Their ingenuity in devising innovative ways to understand and visualize our galaxy laid the foundation for contemporary space exploration and astronomical research. Long before the age of advanced technology and space telescopes, ancient civilizations observed a peculiar celestial sight, a vast, elongated arm adorned with colorful star clusters in the night sky during specific months. Unable to comprehend its true nature, they marveled at this phenomenon. Even today, in remote, light pollution-free places like Egypt's Whale Valley, we can witness this awe-inspiring celestial arm, connecting us to the wonder and curiosity of ancient skywatchers. These early civilizations chronicled their observations, logging these sightings in records and star maps. One of the most renowned archives preserving these star maps and their associated star names is Claudius Ptolemy's Almagest. Ptolemy, who spent his life in Egypt, particularly in Alexandria, produced star maps that, while not entirely precise, served as valuable references for astronomers over many centuries. In 829 CE, during the Islamic Golden Age, the Al-Shamashiyah Observatory was founded in Baghdad, marking the first observatory in Islamic civilization. Muslim scientists, including figures like Abu Rayhan al-Biruni and Muhammad ibn Musa al-Khwarizmi, made significant contributions to astronomy. They discovered stars and classified them, enhancing our celestial map. This pursuit of knowledge continued through the Renaissance, shaping our understanding of the cosmos. Thank you for watching another episode of Alizeb. While you are still here, don't forget to like and subscribe.